Hello, everyone. I hope you had a good lunch. My name is Yaghi. I'm the Dean of Engineering at USC, and it's my unenviable task to chair a session right after lunch. So I might say, do you want your lunch with AI or without it? I suppose we had our lunch with AI. However, I am extremely honored to introduce our first speaker this afternoon, and that's Professor Omar Yaghi, recent Nobel laureate in chemistry. I think we have to give right now a big round of applause. He told me to stop here and say nothing more about it, but I will not. So he's known for pioneering a new field of chemistry. I'm a chemical engineer, so I kind of know a little bit about this, but not a lot. Reticular chemistry, which he defines as stitching molecular building blocks into crystalline framework structures by strong bonds. The outcome of this chemistry has been metal-organic frameworks and covalent organic frameworks, which are essentially materials that have an extremely high surface area, which means they can absorb tremendous amounts of gases, including water, CO2, and also very useful for hydrogen and methane storage. This approach he developed has led to an exponential growth in the creation of new materials. He has published over 300 peer-reviewed articles on these materials, and they have received a total of more than 250,000 citations. I know that, collectively, 10 top scientists don't have more than 250,000, so you can understand the impact of that. Professor Yaghi is elected member of the National Academy of Sciences and the German National Academy of Sciences Leopoldina. He has received tremendous numbers of honors. I should mention just a few of them. The Tank Prize, very recently, the Wien Future Prize for Emerging Science and Technology. I know both of them because I happen to be on the selection committee, and many, many other prizes like the Royal Society of Chemistry Centenary Prize, King Faisal International Prize in Science, Albert Einstein World Award of Science. Tremendous accomplishments. Please welcome Professor Yaghi.
Thank you very much for the generous introduction, and I want to thank the Chen Institute and Chrissy for putting this together, and I also want to thank Jennifer Shays for helping with the organization, for being part of the organization, and it's a pleasure for me to be here to share with you some of our initial results in the use of AI to make materials. Okay, so I wanted to just say that a new field of AI for materials is emerging at UC Berkeley, and it's done in collaboration with Jennifer Shays and Christian Borgs and many others as part of our newly created Baker Institute of Digital Materials for the Planet. This is a 3-year-old, now almost 4 years old, institute that we have been where we have been experimenting and developing AI models for AI for materials. So I call it AMATRY, AI, materials, MA, and TRY, like in chemistry. But it is really my initial definition for this new discipline that is emerging from BIDMAP is the science of using AI for the design and synthesis of materials and for connecting a property to a specific chemical structure. This is one of the biggest, let's say, challenges facing us today, is not only how do I take a structure and find out what properties does it have, but also if I want a certain property, how do I go back and identify a structure that would do just that? That's the challenge that we're trying to ultimately address. So why AMATRY now? Why is it so interesting now? And why are we interested in this? So because we just figured out how to put building blocks together to make crystals, well-defined materials. And the challenge that we had to overcome is the ability of things when they come together to break apart and then come together again to make a more ordered system. So that's the thermodynamic reversibility that you need. But once you've done that, then the kinetics takes over, and you want the kinetics to be just right so that you can build large enough units. If it's too slow, you will stop at small aggregates and not crystals. If it's too fast, then you'll make disordered structures that would be ill-defined rather than crystals. So that challenge we have addressed and figured out in plain words. We discovered the recipe for making crystals when you're stitching together molecular building blocks. And the Nobel Committee was correct in citing this structure, which shows the inorganic part, the zinc-oxygen junctions linked by what, as you will see shortly, by organics. The amazing thing about this structure, MOF5, Metal Organic Framework number 5, is that, as they say there, this is actually the words of the Nobel Committee, is just a couple of grams can hold an area as big as a football field. Okay? Just one, in fact, right now, we actually do better than that. 1 gram of a MOF, which is no larger than an American sugar cube, contains as much space as an entire football field. And so the inside is much larger than the outside, and that is the power of being able to design materials on the atomic and molecular level with precision. Not only can we make materials that have high surface area, but we can also adjust their porosity. Adjust it, we can make it larger as we wish, as large as proteins could be used as guests inside these pores, but also as small as hydrogen molecules that could be compacted in the pore. And furthermore, when functionalities are put on the organic linkers, you thereby craft the interior of the pore chemically so that you can target a specific property. So the Nobel Committee cited the development of metal organic frameworks. They didn't cite covalent organic frameworks, okay? But we do have a field that is raging out there called covalent organic frameworks that we developed, or we were the first to develop back in 2005 and 2007 for 2D COFs. Covalent organic frameworks are made entirely of organic molecules linked together by covalent bonds. There's no metals in this class of materials. But this also, as you'll see shortly, these compounds are very important for capturing CO2 from air, and they are the only ones that are able to do this in an energy efficient, potentially economically viable way. We have also, I'm trying to show you the wonders of this field, that they're not just drawing on a page, they are real. These are real materials where we were able to interweave organic threads in and out of each other. And that's what this chemistry really allows you to do, is that once you know how to do these intersections, you can link them together to make a woven structure. And these are turning out to be extremely important in terms of improving the mechanical properties of materials. So there is plenty to do beyond MOFs. And a lot of it can be aided by AI. For example, we are able to take the active site of this enzyme TEV protease, which is programmed to cleave this amide bond. And just by throwing these amino acids, attaching them to the backbone of the MOF can do exactly the same thing, okay? And that's because this heterogeneous interior of the MOF has local arrangements that are similar to the enzyme, and indeed, It's just this enzyme and this MOF are the only objects that we have that could cleave this amide bond and only this amide bond. This is extremely powerful because it means that the interior of the pore could be functionalized in a heterogeneous way, and still you can obtain properties that are like the enzyme, except the MOF can work under much harsher conditions and a wide range of conditions compared to the enzyme. So how does Ametry accelerate reticular chemistry? Okay, first, materials discovery, right? That's very important. If you don't have the material, you can't get to the property. Second is we want to predict properties, but as I said before, we want to go from a property to a structure. And third, we want to simplify our laboratory tasks, okay, so that we can get there faster. Okay, so as I said, BIDMAP has been an incredible catalyst in this work, and I work with a group of people at BIDMAP. Jennifer Shays was the founder of this institute with me and Christian Borgs, and the three of us have been collaborating over the last 3 years on developing Ametry. We have published together about 20 or so papers already. We were the first in chemistry to introduce the use of LLMs to make chemistry agents that can synthesize and that can, as you will see, instruct students on how to synthesize and discover materials. Okay, so I'm going to show you 4 examples, very quick examples of our preliminary results. This is just the start. They can get better later, but this is just a taste of what might be possible. The first example came back, we published the first paper in 2023, and it's about text mining. Okay, so one of the things that we wanted to show is that ChatGPT can mine information accurately. And you can see here that we had a strategy, I won't describe too much, but it's written here, of prompt engineering and then asking ChatGPT to document. This experiment had 250 papers that we asked ChatGPT to go in these scientific papers, in the synthetic section, the experimental section, and to pick out this information from the preparations, okay? Like the compound name, what kind of metal is used in the MOF synthesis, what kind of linker, solvent, temperature, and the time that is required to make the material. And it did that. It took about 2 weeks to go through those 250 papers because at the time the students were cutting segments of the papers and putting them into ChatGPT. Now this experiment will take hours because they can do it automatically. But the result of this experiment was that the text mining by ChatGPT was quite accurate, well over 95% accuracy, and many of the inaccuracies were because the authors had placed some of their data in the abstract or inappropriately in an inappropriate section in the paper. Okay? And based on that kind of information, we were able to predict, or ChatGPT was able to predict the synthesis of many, as you see, many of these MOFs accurately. This is quite powerful because it means it's not just can recall the information, but also from a PI point of view, the researcher now has the facts in front of them, and they can make decisions on what observations to pursue based on facts. In chemistry, I don't know how many chemists are here, but in chemistry we have something we call chemical intuition. And I, as a professor with students in my lab, we use our chemical intuition sometimes to advise students under what conditions they could carry out a reaction or, in our case, a crystallization. Some of this chemical intuition is also expressed in the interaction between a senior graduate student and a junior graduate student. Well, it turns out that this chemical intuition is largely wrong because it's not based on facts. When you ask somebody in chemistry, why did a reaction not work? They will give you many reasons why, but if you go through each one of those reasons and you ask them, have those reasons been proven scientifically? 100% the answer will be no. So it means that we have been doing chemistry without all the facts before us. So this ChatGPT experiment shows that, in fact, once you have all the facts, all the experimental facts before you, you can make much better decisions. It's much better than chemical intuition. So I'll skip over that. Example number 2 is molecular editing by ChatGPT to improve the water harvesting properties of moths. So this is a moth that's made from zinc and pyrazolate dicarboxylate, a readily available component. Zinc and these organic linkers are readily available, and it has tunnels, and in these tunnels you have patches of hydrophobic and hydrophilic centers, okay? So if I am a water molecule, in this case, water is going to be flowing inside the pores. So if I am a water molecule floating inside the pore, I am looking at patches, infinite number of patches alternating between hydrophilic, water-loving, and hydrophobic, water-hating regions. And you'll see in this movie, which is real, it's actually based on single crystal X-ray diffraction data. We know exactly where every atom in the framework is located, as well as where every water molecule is residing in the structure once it starts attracting water. But what I want to say is that you'll see in the movie that the first water molecules naturally go to the most hydrophilic regions. And when those regions, when those patches are filled, more water molecules bridge over the water-hating region, the hydrophobic region. And this push-pull interaction with water, between the framework and water, allows you to not only take in water, but also remove the water under mild conditions, 45 degrees C. From the world where I was born and raised, well, that's sometimes midday temperatures, okay? So that meant that I could use a powder of this moth at night to take water from the air, and during the day when it heats up, if I put this in a box, when it heats up, water comes off and it condenses to make drinking water. And that's exactly what we have been able to do. And now I'm going to show you the magic of this moth in how it attracts water to its interior. I'm excising one channel out and slicing it so that now you see the hydrophilic regions take up the first water molecules. The hydrophilic regions are filled. Now more water bridges over the hydrophobic regions, and thereby filling up the entire structure with water. This framework takes about 50% of its weight in water. It's already commercialized to extract water from desert air. Desert air normally has humidities, relative humidities of 10% to 20%. So a moth that takes up water in the desert will take up water even in the humidified regions where there may be plenty of water, but it's not clean. So in fact, this moth works in almost anywhere in the world at any time of the year. Okay. My vision is that we use moths to give the world, individuals, citizens of the world, water independence, where you have control of your own water because you have the moth and you have the moth device that delivers water, and you're in control of the water, you're in control of the quality of the water that you're getting. And so my heroes, my students, took that moth to the desert and showed using a device like that contains, basically made up of slices or, let's say, pancakes of moth. And as I described before, during the night, the device is open to air. It takes up water from air. During the day, it heats up, and then water comes out, and you can collect the water. And that was done in Death Valley, okay? So it just shows you that the MOF can attract water from even the driest of deserts. The MOF will work for many, many years. Okay, it's graded for 6 to 7 years without having to regenerate or to replenish the MOF. Okay, and at the end of the MOF journey, you can separate the metal from the organic and reassemble it in water with zero discharge process. So it's entirely, the making of the MOF and the use of the MOF is entirely sustainable, and there is nothing emitting CO2 in this process of water harvesting. Okay, so ChatGPT, once you have that, you can ask ChatGPT to give you better organic linkers that may give you more water, right? Because as I showed you, water uptake depends on the composition of the interior. And so it went through the different iterations of putting different atoms around the ring, okay? And we made these compounds, okay? You can even have mixed linkers, and we measured their water harvesting properties. And I don't want to describe all this stuff. It's just studying the water uptake properties. But what I want to say is that these, we call them long arm extension MOFs, LA MOFs, turn out to be the very best MOFs ever made for harvesting water from air. So clearly, ChatGPT is helping in this regard and helping us get there a lot faster. So this, as I said, this is already one of these long arm MOFs is already being commercialized by a startup in Southern California, and we're looking at delivery of 2,000 liters per day for these devices, okay, with incredible energy efficiency. Okay, so this is an electrified device. It's the most energy efficient device for delivering water. Now, the experiment I described to you about the desert, it didn't use electricity. It just used ambient sunlight. Well, this one does exactly that, and it delivers 850 liters of water per day. Okay, and these, you can make them larger, you can make them smaller. The MOF works the same way. The MOF works the same way, whether it's in the desert or in the humidified region. In fact, in the humidified region, it works a little bit better because there's more water in the air. So I think that this is very, very exciting, and part of the development is aided by ChatGPT. Okay, so example number 3 is that my students said, okay, we'll make an entire research group out of ChatGPT agents. So that's what they did. They went in and, let me see if I have another slide here. Okay, well, that's not, yeah. In this example, they use 7 agents. Each agent is doing something like literature search, planning the synthesis, advising, so replacing me in the equation, reprogramming the robot so that it does the right reactions, 3D printing the apparatus or the containers that we use in the synthesis, and analyzing data. So we have 7 agents collaborating as an entire research group to crystallize the MOF. Okay, so in this example, I'm going to talk about COF, not MOF actually. COFs are notorious for the amount of time that it takes to crystallize them, and not because it takes long to crystallize, it's because we're using a lot of trial and error methods, and so a typical researcher sometimes takes years to crystallize a new COF or to obtain a COF in crystalline form. So definitely this was an area that we could improve on using AI techniques. So here we targeted this COF that was made in my lab by Zihui, and it's basically a COF that's made entirely of carbon-carbon bond backbone. Those are some of the strongest bonds known in chemistry. And the reason I'm emphasizing that is that when you're trying to take the whole planet's Earth and passing it through the COF so that you can capture the CO2 that's in the air, that extra CO2 in the air, you need incredible stability. And there's nothing more stable than carbon-carbon bonds that make up diamond to do this, okay? There are many, many materials that are being investigated for CO2 capture from air, but nothing does as good as this, as well as this material entirely because of the carbon-carbon bond backbone, which taken us 18 years to invent the chemistry that allows us to crystallize these. Then inside the COF, you have amines, polyamines. These are largely primary amines, and these are the units that will seek out CO2 from air. That separation of taking CO2 from air, you're trying to separate for each CO2 molecule, there are 2,500 other molecules that you want to leave behind. So you're trying to separate one molecule from 2,500 molecules. It's a very difficult separation. These amines potentially can do that. So this is the experiment. We took Berkeley air, open air from Berkeley, and passed it through a solid of this material. And we measured the CO2 concentration in the air. You can see it's hovering around 450 ppm. We also looked at the humidity. Okay, you can see the humidity in Berkeley air. And this is the uptake. This is the uptake by our material. And you see that it scales with the humidity. The higher the humidity, the better the uptake, because water allows us to shift the equilibrium towards the CO2-bound species, or to have more CO2-bound species. But if you look at this material, its behavior, if you look at one humidity level, its behavior is consistent at that specific humidity level. So this was the very first material where somebody used real air and cycled over almost 19 days and showed that, in fact, the material behavior is consistent. This is an amazing development that is now, we are trying to scale up this COF. We're trying to make it cheaper, and we're using AI methods to do that. But there's nothing that it behaves like it. So the very first step is, how do we get these COFs to take less time for the researchers to crystallize them? And so we targeted this COF. Okay, this is not such an easy COF to crystallize. And this is the 7 agents that collaborated to crystallize the COF. And you can see here, by experiment number 9, you have no crystallinity. When you get to experiment 84, you have full crystallinity of the material. Okay? That means that what has taken a student or a researcher 2 to 3 years, you can do, this experiment took 2 weeks. Okay? So these techniques, these AI techniques, are transforming what we do, at least in my lab, and for certain will transform what chemists do. Here's another example where the entire community tried to crystallize this COF, and all they can get is this kind of crystallinity. This is about 100 groups around the world. Now, with just ChatGPT, you can make, these are 3 different groups. With ChatGPT, I won't go through this is what the students are telling ChatGPT to do, okay? They're putting in information, they're trying to, so you can say, you are a reticular chemist developing this kind of COF. We have a robotic platform that's going to execute what you give us in terms of reaction conditions. Our objective is to conduct the literature search and develop reaction conditions, and we expect you to give us 96 conditions, because that's what the 96 wells that for the high throughput are requiring. And then they go on, select the precursor, stoichiometry, select the reaction temperature and time, select the family of solvents and catalysts. So it's exactly what we do in the lab, but ChatGPT is going to do this. And these are the different solvents and the conditions, and we run those. We run those in terms of high throughput robotic, and it's shown here. We have, many of you probably know this. we do it automatically, just like whatever the researcher is doing, now it's dedicated to this automated platform, and the result is that you get much better crystallinity than the entire community. Okay, it took the students 3 weeks to do this. 3 weeks because they had to play with the robot and make sure all the glitches are solved. It has nothing to do with chemistry. So this is really a revolution, at least in reticular chemistry. But the ramifications of it are amazing for me. So let me see what's on this slide. Well, that is it. Okay, so in experiment number 4, and the example number 4 is that we want to build a platform for molecule to society. I have shown you the example of water harvesting. That was all done in my lab, where we went from the molecule to the material, configured the material in a device, then studied the device, made sure that it's energy efficient, it's optimal mass transport, optimal energy transfer in the device, and ultimately the device went into commercialization. That's what AI is allowing us to do. It's allowing us to go from a molecule to society. And that's why we created AIAS. AIAS is a startup that is now incubating in BBH, in the Baker Biohub at Berkeley campus, right at the edge of Berkeley campus. And our aim is ambitious. We want to make materials better, cheaper, faster, and greener. Okay? And we want to be able to do this by going from molecules to society. And we conceived of 3 components, 3 cycles. The first cycle is generative predictive. It predicts what kind of moth you want or cough. The second one is a synthesis, as I just showed you, robotic, also powered by Gen AI. And then we have a third cycle that not too many people talk about, and that's the scaling cycle. Without the scaling cycle, you're not going to reach the world. You're not going to reach society. And so we have these 3 cycles, and depending on time, I could describe what goes on in these cycles, but just to give you an idea, you input a chemical formula of the different building blocks that you want to assemble, and you could also put in a desired property. You could say, I want a great water harvesting material that's cheaper than what's out there, that's performs better. And it comes up with a whole bunch of structures. This generative model, in our case, one of the models, the diffusion model, it gives you hundreds of thousands of structures. Then we have different techniques to optimize and get down to the most synthesizable structures. These are about 24, let's say. So that's our design generative AI predictive cycle. Then you go into, for these synthesizable structures, you go into a synthesis planner that gives you reaction conditions under which to make it. And then the automated synthesis takes over, automated characterization, and so on. In the end, you have a synthesized chemical structure that you can compare to the original structure that you targeted. And if you're successful, then this goes into the data set, but then it follows the path where your material can now go into industrialization. You put it in different form to go into a device that's going to deliver the properties and deployment into society. And then all these different cycles feed into a data set that gets better and better the more, of course, you go around these cycles. But in my lab, we've made these 3 cycles work. Okay, they work separately from each other. And at AIAS, we're trying to get them to work together. And so we have a great team of about a dozen employees, and plus a total of 20 people working at AIAS to get these 3 cycles to work together. So it's very inspiring and very exciting. And it is transforming the way we make materials, but also the way we can go from a property to a material. The result of just the first 2 cycles, when we made the first 2 cycles work together, this was the result. We took we did 2,688 reactions in a field that I didn't mention, but we invented in 2006. It's called ZIFs. They're special metal organics. And the result of that was that we can discover ZIF. I have to tell you, ZIFs is a well-farmed area in our field, okay, meaning that an investigator wanting to make a new ZIF would have a hard time making a new one because it's just so many people are in the field that all the things that could be made potentially have been made. So we challenged ourselves and said, let's take this well-farmed field and see how do these models work. And we can discover, our discovery rate doubled from what my students and others are doing. So per well, when you use the machine learning algorithm that has been conditioned for this, for ZIFs, you get double the discovery rate compared to the reactions where there was no machine learning involved. And so you make new ZIFs that haven't been made before. Structures, same structure, but with different functionality. And you also can make, based on the linker, you can target different structures. And to me, the amazing part is that you can make unexpected structures. Okay, things that an expert like me would look at and say, wow, I didn't expect that to happen. I didn't expect that could be made. So it's very clear that we have something very special here that seems to be very effective at what a synthetic chemist like me, who's interested in materials and materials properties, could do. Okay, I guess that's the end. My great students, I want to acknowledge them. They are really amazing. Berkeley students are absolutely amazing students. They are able to think outside the box, and they're very agreeable to doing the experiment, okay, which is the gateway to discovery. And of course, I want to acknowledge the funding agencies that have helped us get here. Thank you very much for your attention.
Thank you, Professor Yaghi, for a fantastic talk. Appreciated learning all these wonderful new things. We have about 10 minutes for discussion, and if there are any questions, please. There's one down there.
Professor, I'm totally a layman, so forgive me about ask very superficial question. When you're actually tasking 7 agents for 7 different functions, is that based on the last figure, design, synthesis, and scaling? Or actually is that you feel like you have 7 students or postdocs that they better have a well-defined task for that? Or is this minimally necessary to carry out high quality and high quality work?
I think what the students did in that experiment, they asked ChatGPT to make an agent that could do these 7 different tasks, okay? And these tasks can work together, okay, during this, but no, it was not subjected to the last 3 cycles I showed. This was a separate experiment to show the power of ChatGPT in streamlining the experimental tasks.
But from your PI point of view, is that necessary to divide into 7 separate agentic activities?
It may not be. There must be another way of doing it. This was our first experiment. It's necessary that we do this because the students or the researcher is doing a lot of trial and error during these processes. And this eliminates a lot of the uncertainty around the trial and error. And in many cases, it allows you to not just have the results and the facts in front of you, but also it allows you to go beyond the sub part of the space that we are exploring. That's really why we have been very successful, is because once you have the facts, you can go beyond what the chemical intuition was telling you to do. So you can explore larger space.
Next person.
So fantastic talk. Thank you very much. I'm an NLP researcher, and as you know, large language models are notorious to be not very stable when it comes to prompting. So I'm wondering whether you have any results that investigate how, as you change the prompt, and in fact, if you change and you use different large language model beyond ChatGPT, there's Llama, so how does that change the result of the agentic setup that you have?
That's interesting. I mean, you have to look at our papers. The answers to your question are described in the supplementary information in our papers. But all I can say about that is that it's like a baby. You have to teach the baby a little bit and hope that the baby does something beyond what you taught them. And so I think that's why I'm always saying that we need to experiment with these models, because as we experiment with them and make them more and more intelligent, so there are a lot of challenges, right? You don't just write a prompt and get a correct answer. You have to play with the prompt. You have to be sophisticated. And I read some of these, but some of our prompts are a page long, maybe even more. So we have published all the details in the supplementary information about what the students have tried and what worked, what didn't work. We also published recently a comparison between like 4 different LLMs. Right. I'm happy to forward those to you. Yeah.
Thank you very much.
But no LLM does everything very well, as you know. Yeah.
Professor Yaghi, congratulations on getting the special parking permit on Berkeley campus. And my question is, like, for AI to work, it needs a lot of data, and not just positive data, but also negative data. But right now, our society does not have the mechanism to publish negative data. And with Madam Maldonado, AIAS president here, should we, you have the power and the leverage now to encourage certain repository of negative data in the society, so that can help the world in general. Yeah. Do you think?
Yeah, I mean, no scientist is going to publish negative data because because everybody will say, well, look, that was a stupid experiment anyway in the first place. So, but I think the journals and societies like the AAAS, like the American, in my field, the American Chemical Society, the journals especially can take the lead on this, where they demand both the positive and the negative results to be reported. And the negative results should be documented the same way we document the positive results, and they should be proven as negative results. So I think that the same rigor of reporting should be translated into the negative results. But the way we treat, I just wanted to mention that in our research, we are coupling the computation AI part directly with the experiment. So, and the more negative results you have from the experiment, the better those models get. And I think that's our unique advantage, is that we have both growing together, the AI models and the experiments with the positive and negative results grown and built together from the very beginning. I think,
Mr. Yaghi, I will be asking you a question. I'm really impressed with your talk, and then I didn't even know a lot of things that I got to know today. I had a question regarding where you talk about MOF that is attached to the active site of the TAP proteases enzyme. What was the motivation to make that molecule, and how did you attach it to the MOF? If you can put some light on it, it would be great.
This is really a very large field to be developed in chemistry, which is how do you have heterogeneity within order? How do you have disorder within order? Okay, chemists are used to, or a major part of chemistry is about making sure you have a pure material, right? Every chemist spend majority of their time trying to make a pure material or trying to make an ordered material. And it turns out that pure material and ordered material are not really the best scenarios for functionality. So the motivation behind that experiment was to show that if I have an enzyme crafted to clip off that specific amide in a peptide, could I, by just random attachment of approximate amino acids that are approximating that active site of the enzyme, if I introduce them covalently onto the ordered backbone, now I have a forest of arrangements, billions and billions of local arrangements in the pore that are what I call the heterogeneity superimposed on the order. And if I'm a substrate and I'm passing through that environment, I am experiencing different local arrangements, and some of which act like the enzyme, because there are billions and billions of them in each granule. So some of them are fertile to do exactly the same as the enzyme. I know it's not elegant, but it's functional, right? So that's why this is an incredible AI computation problem, is how do we figure out what is happening inside this, in this heterogeneity that makes it operate. In other examples, for example, in the separation, it operates much better than the sum of the parts. So it means that there is some emergent phenomena going on inside the pores as a result of this heterogeneity.
Thank you.
Good.
Thank you.
It's you.
Hi.
No.
Thank you for the presentation. I was wondering, so you mentioned that very interesting sort of dehumidifier-based approach for extracting water from the air, and you mentioned like power efficiency ratings for the like actively powered version of it, like 0.3 kilowatt hours per liter or something like that. And I was wondering if you could like, I don't have much context on like what that means and how it compares to, say, reverse osmosis desalination. So if you could provide a bit more context on like how that compares to alternative methods in terms of efficiency, and also maybe like how much more efficient do you think it can be made as we further improve the quality of the MOFs used in the design and like further mature the overall design itself into which those MOFs are embedded?
Okay, so the devices that deliver 850 liters per day require no energy at all, no new energy, okay? Meaning you are just using ambient sunlight and waste heat. So that means that it's costing you 0 kilowatt hour per liter. And so it's free. Now for the electrified device, the one you refer, I gave the number 0.3 kilowatt hour. Yes, it's more expensive, maybe an order of magnitude more than desalination. But the value that is brought to you as a consumer is immense, because you're no longer attached to the grid, you're no longer putting brine in the water near these plants, and you also have the security of having control over your own water. Not just national security, but also personal comfort that the water that you're getting, not only are you using it independently of the grid, but also, so it depends on the cost, depends on the value, or the cost of the device is going to depend on the value of what you're doing. We think that for the electrified device, the use is really for data centers that require water and they require cooling. That's a major, major application for this technology. But the one that doesn't use any energy, the passive devices, they can be located anywhere in remote areas, on islands, and in your home with no energy input aside from ambient sunlight.
One final question.
Great talk. I'm not working in this area. That's why it's an eye-opening talk to me. One naive question is about one example you gave us. extracting the carbon dioxide from the air, use the COF method. So usually I know we can use a physical method, reduce the temperature, get the carbon dioxide immediately. Of course, this is probably low energy efficient. My question is, for this material, how expensive they are? And when you extract the carbon dioxide, eventually it will saturate. Then you need a release to reuse. So compare these two procedures. Which one is more reasonable for current application?
Good question. So you take up the CO2 from air. That's the hard part, right? That's a very difficult separation, but we've overcome that. Now your cough is filled with CO2. Now the nice thing about coughs that I didn't mention is that we can modulate how strong the CO2 is bound into the pores. And so in this particular case, you only have to heat the cough up to 50 degrees Celsius to remove the CO2. That's waste heat. That's a heat you can get from waste heat in industry, right? So that's not costing you any energy, any new energy, right? That's great. And so you do this and you cycle, right? You take the CO2 in, you take it out, and you start another cycle of CO2 going in. So based on that compound, by the way, which right now is slightly expensive, but that's just the beginning. Our AI models in ematics is going to make a cheaper one. It's going to find building units that are even cheaper than that. We already can make it 30% cheaper than what you saw here. Okay? So this is just the beginning. And what I really wanted to say is that in the air right now, we have about 1,100 gigatons of CO2, extra CO2 that we need to take out of the air, okay? And using this cough, if I put a plant of 100,000 tons of this cough in 600 cities around the world, cities that are about 1 million or more, we can take that CO2 out of the air in less than 3.5 years, okay? So we have the scientific challenge of binding CO2 from air is solved. The rest is having to make the material cheaply and scale it up, and that's what we're doing in these in some of the startups that I've mentioned.
On this wonderful note, thanks again.
Yeah, thank you.